The exciting topic for this episode is work, not the type of work that we talk about in day-to-day life, but the physics definition of work. You'll notice a lot of textbooks start out their discussion of energy by looking at work. I wanted to look at types of energy first, and now we're going to go back and get to work. I think it makes a little more sense that way. Here is how we are going to define work in a physics sense. Whenever you are transferring energy to an object or taking energy away from that object, then we say you are doing work on that object. So positive if you're giving it energy, negative if you're taking it away. The way that you do that, the way that you give or take energy from an object, is by exerting a force on it. But there is a little caveat here. That force has to be affecting its motion. It's kind of easiest to understand if you just look at the equation here. The equation for work is work equals force times distance. So if the object is not moving any distance, you have 0 there for d, then you are not doing work on the object. So if you are pushing on a wall, you are not doing any work on that wall. You're not giving energy to that wall. If you lift up a box, that box moves, so you did work to lift it. But then if you're holding it in the air and not moving it, you are no longer doing any work. And you might say, well, I get tired, I'm exerting myself. And the reason for that is if I'm pushing against a wall, my muscles are kind of flexing and then relaxing, and so there's little micro movements, there's little distances that my muscles are doing, so energy is actually being transferred kind of internally in my body, even though I'm not transferring it to the wall. Whereas I could say lean a ladder against a wall, and that ladder is going to be exerting a force on that wall, but that ladder is not going to be losing any energy because there's very little motion at all internally in those materials. Now these little lines here, these represent parallel. That's just one little added complication, that it's only the force you're exerting in the direction that the object is moving that does any work. So if you have a force at an angle, you have to take the component in the direction that it's moving to calculate the work done, and I'll show you that in an example. Let's start out with some simpler examples though, where our forces are not at angles. We're just going to be pushing a box along the floor. Looks like a bit of a dented box here. Let's say we've got a 20 kilogram box, and we're just going to be exerting a force this way. Let's say it's a 100 Newton force. Other forces acting on the box, there's going to be gravity down, there's going to be the normal force up, and this isn't writing very well tonight. Okay, and let's say that it's frictionless. We are on a frictionless surface. Oh my goodness, that's a terrible line. Well, we'll live with it. Okay, so as I'm pushing this box, the amount of energy I give the box depends on how far the box moves while I'm pushing. So say let's say that the front of the box starts here, and the box ends up, my terrible lines continue, ends up moving 5 meters this way. So the front of the box is now over here, and it shrunk a little bit. Alright, if I want to find the work done, well, I've got these different forces. I could find gravity by doing 9.8 times the mass, but gravity is not in the direction that it is moving. Neither is the normal force, so neither of those forces are doing any work on the box. The only force doing work is my horizontal push, so all we have to do to find the amount of work is do force times distance. Force is 100, distance is 5, and we get 500. Now the units of work, since it is the amount of energy you transferred, has to have units of energy. You might think, well, this was newtons times meters. Well, 1 Newton meter is equivalent to a joule of energy. So we have 500 joules of work that we did on the box. 500 joules of energy that we added to the box. Well, where did that energy go? The law of conservation of energy says it can't just disappear. The box can't just, suck it in and hide it or something. The box, if it were initially at rest, it would now be moving, and so it gained kinetic energy, and in fact it gained 500 joules of kinetic energy. We could figure out how fast it was going by setting 500 equal to our equation for kinetic energy, 1/2 times mv squared. Mass of this guy is 20, and we can solve for v squared, so I'm going to have 500 divided by 10, so I'm going to have v is the square root of 50, which rounds to about 7.1 meters per second. Is how fast that box would be going if we pushed on it with a 100 Newton force over a distance of 5 meters. So pretty basic stuff there. Now let's look if we are lifting a box. If I have this same 20 kilogram box, maybe a little less dented this time, and I'm going to lift this thing up. So the bottom, let's say it's 2 meters high now. Lift it over my head a little bit. Well, how much force does it take to lift this thing? My lift force has to balance with gravity, right? So we can find that by doing 9.8 times the mass, and that is the force required to lift it. Now you might say, well, if the lift force equals gravity, it's not going to go anywhere, and you're right. So technically you have to lift with a little bit more than this to get it started, and then once it gets started, you can lift with a force equal to gravity to keep it going. But once you get to the top of the lift, you're going to stop lifting, and the box is going to slow back down to a stop. So at that point you're lifting with less than gravity. So the fact that you lifted with a little bit more at the beginning and a little bit less at the end actually averages out to lifting with a force equivalent to gravity for the entire time. So we can find the work done. Sorry about that. Go away, I've asked. Thank you. Alright, so we can find the work done by looking at our lift force times the distance that we lifted it. So that was 9.8 times 20 times the distance of 2, and that works out to be 392 joules of energy it took to lift this box. Now in this case I said I lifted it up and then it stopped, so it's not moving anymore. So where did this energy go? Well, you can think about it two ways. That if the box is not moving, it didn't go to kinetic energy, but it is now higher, so we can say that we gave it gravitational potential energy. Another way to look at it is to say, while we were lifting up on the box doing 392 joules of work, gravity was pulling down on the box doing negative 392 joules of work, because it was pulling in the opposite direction. It was taking energy away. So we could say that the box, that as we put energy in, the gravitational force took energy out. Now when we let go, gravitational force is going to give that energy back. Gravitational forces are like that. Whatever energy they take, they give back, and we call those conservative forces. We'll talk about those in more detail another time. Alright, now that brings us to another idea where in that situation where we lifted the box and exerted a force on the box and gravity exerted a force as well, there was more than one force doing work at the same time. So we have a concept similar to net force where we say net work, which is the overall work being done by all the forces. So we can look at this equation here where we just add up the work done by each force separately, whether you just have two or however many forces happen to be acting, and that's going to give you the overall energy that was given to or taken away from an object. Now since each work component, each work term in this equation is each individual force times the distance, you can write this equation out as F1 times distance, F2 times distance, and on however many forces you have. All these distances are going to be the same because this is the distance that the object moves during the time that you're considering it. So we can factor that d out and we get just adding up all the forces. Well, adding up all the forces is finding the net force. So sometimes it's easier to do it this way depending on the information you have. Sometimes it's easier to do it this way. So you can find net force first, multiply by distance, or you can find the work done by each individual force and sum that up. They're going to give you the same answer. And this is known as the work kinetic energy theorem here. The net work is always equal to the change in kinetic energy. So if we jump back to this situation here, the amount of positive work that the lift force did was equal in magnitude to the negative force that the negative work that the gravitational force did. So the change in kinetic energy was 0 if it was stopped here, even though it had some kinetic energy in the meantime as I was lifting it, but then when I stopped lifting it and it stopped again, the change in kinetic energy was 0, and that's because the net force was 0, right? The lift force was equal to gravity, at least on average, so the change in kinetic energy is 0. Let's look at some other examples where that's going on. Let's go back to our 20 kilogram box. I'm getting better every time. And I'm going to still have my 100 Newton force pushing it this way. There would be gravity and normal, but we don't really care about those. But let's say now, instead of having a frictionless surface, we're going to add 80 newtons of friction opposing our motion. We're still going to move the box 5 meters. And now let's look at the net work done on the box. I'm going to do it both methods just so you can see. This would be the work done by the push force plus the work done by friction. Okay, the work done by the push force is going to be 100 times 5. The work done by the friction, I'm going to put it negative here because this force is in the opposite direction. So negative 80 times 5. And so we're going to get 500 minus 100 equals 400 joules. Sorry, bad. I was thinking ahead there. Okay, so 80 times 5 is 400, so 500 minus 400 leaves us with 100 joules of energy is the net amount of energy, and it's positive. That means energy went into the box. The other way we could do it is with the net force times the distance. The net force is 100 minus 80 times our distance of 5. It's kind of an ugly 8 there, but alright, 100 minus 80 is 20 times 5, and so again we get the same answer. Usually it's probably easier to solve it this way unless you get confused. Kind of conceptually you can see what's going on with the energy a little more clearly with this situation here, but the calculations are a little more straightforward with this approach. So we get 100 joules either way, and where does that 100 joules go? Well, we know that the net work is equal to the change in kinetic energy, so if we assume this was initially at rest, then we can figure out how fast it was going by setting 100 joules equal to 1/2 mv squared. Okay, so this is going to be 10 over here. We divide there. We're going to get v equals the square root of 10, which works out to be about 3.2 meters per second. So when we worked out this same problem without friction, the box ended up with 500 joules of energy, just this 500 here, which gave us a velocity of 7.1. Now that we have friction removing some of that energy, we're not going to be going as fast after that 5 meter distance. Now you could figure all of this out with forces and kinematics and stuff, but I want you to practice doing it with energy so you get the hang of this. And plus a lot of times it's going to be simpler to do it with energy. Alright, one more example here. We mentioned back at the start here that this force parallel times the distance thing is sometimes important. So let's look at our 20 kilogram box one last time. It's moving over to the left a little bit for some reason. And instead of pushing it, we're now going to be pulling it. Let's say we're still pulling with 100 newtons, but now we are at a 30-degree angle here. And let's say we still have 80 newtons of friction. Gravity and normal are going to be there, but they're not in the direction of motion, so it doesn't matter. In this case, if we want to find the net work done on the box, I'm just going to jump to the net force perspective or approach. So the net force isn't going to be 100 minus 80 this time. It's going to be the x component of the pull force minus the friction, okay, times the distance. Well, the x component is going to be 100 cosine of 30. minus friction, which was 80. Let's still say that we pulled this box 5 meters. So we're going to have this whole thing here, which is our net force, times our distance of 5 meters. 100 cosine 80 is 86.6. Sorry, 100 cosine 30 times 5. So this is going to be 6.6 times 5, which works out to be 33 joules of energy. So if you remember, the first time we had 500 when we just had the 100 push force this way. Then we went down to 100 when we added friction. Now we're down to only 33 joules if our force is not focused in the right direction, so to speak. Only a component of this force is doing work. And you could go ahead and set this equal to 1/2 mv squared and find the velocity, but that's a little trivial at this time. Alright, so have fun doing work, everyone. See you next time.